All right.
So if you could both just mute just now, please, and you can turn off your cameras as well. Hi everybody, welcome to this next IBPSA Education webinar. We've got lots for you in the run-up to Christmas, and I'm delighted today to introduce PC Thomas, who is going to be talking about end-of-life HVAC plant upgrade. It's really exciting to have a webinar about building performance simulation being used with existing buildings and in the context of this end-of-life HVAC replacement, which in fact resulted, I think, in a 46% energy saving. So a real demonstration of the value of performance simulation in that context. So this is part of the webinar series that's presented by the IBPSA Education Committee. I say this every time, but just in case anybody's new, the committee exists to identify training needs. So if you think there are needs that we're not meeting and that we could do, then please do get in touch. We also want to initiate, develop and encourage new educational materials and methods. So again, if you have ideas about that, please do let us know. And as always, this session, in the same way as all of our other sessions, are open to members as well as to non-members. So we'll be posting the recording of this session on our YouTube channel afterwards, and we'll let you know where that is so that you can have another look at it if you would like. So the format today, I'm going to ask you some quick questions, then I'll invite PC to give his presentation. If you could please use the question and answer box at the bottom of your screen to put any questions that you have in, and then at the end of the presentation, I'll put those questions to PC, and then at the end, I'll tell you a little bit about our new webinars that are coming up. So I'm just going to launch the poll. Please do tell us what you would like to see more of. So you should be able to click on that. If you have any problems with that, please let me know. You can put your hand up and let us know what your I will relaunch that and see if that will help. Okay, so please do let us know, firstly, in what role you use building performance simulation, where in the world you're based, and what topics you would like to see in future webinars. These are all really helpful for us in planning the materials that we put forward and understanding what our audience is looking for. So PC, while the audience are just answering that, I'm going to stop sharing my screen. If you would like to share yours, please.
How's that? Can you see it now?
No, I can't see it at the moment.
Hang on, sorry. Let me do that one more time.
That looks like it's worked now. Yeah.
Yeah, I should see it in a minute.
Great. So thank you very much. So it looks like we have quite a lot of students in the audience. So we've got 56% students, more professionals and practitioners at 28% than we have academics and researchers at 16%. Where in the world you're based, we'll have a good look at later. That's always super interesting. And while PC is talking, we'll have a look at the topics you would like to see in future webinars as well. One extra question from PC is, are any of you involved in the air conditioning industry? So maybe you could raise your hand to let us know. So I think that's one person, PC.
Okay.
The rest perhaps more building focused. So I'm going to end the poll just now, and it's over to you, PC.
All right. Thank you very much. I'll just start my timer for 45 minutes. Okay, great. Well, thank you very much for the opportunity to talk on this topic. And I'm going to focus on the actual process of the end of life HVAC upgrade and how simulation was used quite strategically. So I won't spend too much time on the simulation itself. Now, just before I start, I have 3 roles. I am, I guess, a consulting engineer. So I'm a director at Team Catalyst. I teach postgraduate students, and I'm also a principal at Design Builder Australia, where we resell the software and train peers in its use. In the consulting part of my work, we really concentrate on reducing greenhouse emissions and improving comfort, but we try to do it with some financial outcomes. So you'll see that as we go through the presentation. Now, when we talk about high performance buildings, what are they? So, I've got 2 or 3 pictures of buildings that we've been working on, or we worked on in the past. This one is a refurbishment. The other 2 were new buildings. But in Australia, we have this quite interesting rating system for buildings, and it's called Neighbours. And what it does is it's quite unusual in that it is based on operational outcomes. Okay. So what that means is that in the way that it assesses a building, it's quite neutral to what kind of air conditioning system you might have, what sort of glass you might have, what control systems you may have. It doesn't really care. What it does require is for you to provide 12 months of your utility bills and some data on the area of the building and how many hours it's being used for and so on. And that gives you a star rating. And the other thing that I should say is that because it's a star rating which was started with a medium of 2.5 stars, by the time you get up to 5 stars, out of a 6-star scale, your building is using almost 60% less greenhouse gas emissions compared to a 2.5-star building. So with that sort of background, we'll go forward. There's a couple more slides on Neighbours before I get on to the case study. And this is an interesting one. In the Australian market, and that's not the same as in other markets, we are able to split our buildings into what we call a tenant's part of the building and a building owner's part of the building. And this is based on the way electricity bills are paid and monitored. So the building owner looks after many of the central services and common areas, and that's called a base building rating. The tenant pays for electricity and for lighting and electricity used within his premises, and he can get a tenancy rating. If there isn't metering available to split the two, then we use a whole building rating, which is kind of unusual in Australia. So as you can see, Neighbours was therefore built for existing buildings because you require 12 months of operational energy bills. And it became so successful that developers started to ask, well, how can we, without building a building, how can we get a Neighbours rating? So the government came along and said, well, if you commit to a legal agreement which says that, my building will perform to a 5-star Neighbours performance after it is built and has worked for 12 or 15 months, then you can market your building as having a commitment to work at a Neighbours, whatever rating that you go for. And that forces you to go through an independent integrated approach, a design review, hiring an independent assessor after the building's been operating. And then if you don't make your commitment, then your name or the building's name appears on the website saying this building hasn't met its commitment, which is reputational damage. And that has led to quite a lot of market change and sophistication. Now, the other thing to kind of remember is that none of this happened by chance, and particularly not by sweeteners. In fact, a lot of it happened after the government got involved in mandatory policy. So while the system came out around 2000, almost nothing happened till 2003 when one of the states, the premiers of the state, I guess you could call him a governor in the US or a mayor in other countries, but one of the premiers actually mandated that all government buildings would be Neighbours rated, and suddenly we saw 200 ratings then. And then again in 2010, the federal government or the Commonwealth government got involved and said, well, if you want to buy or sell buildings or if you want to lease office spaces, then you must have a Neighbours rating. And because of that, you suddenly had this huge spike of ratings, which has continued across the years. And what we've learned from Neighbours ratings is that a Neighbours rating is only valid for 12 months. So you have to re-rate the building after 12 months. And if you do that, this is the average of about 2,500 buildings in the database. And what it shows us is that every time you re-rate it, you get a reduction in emissions to the tune of, in the average reduction in greenhouse gas emissions after the 14th rating is about 53%. So it's quite an amazing system. Now, if you look at the whole building and what it uses or what systems use as energy, this is everything that the building owner looks after. All of these are different energy use systems that the owner looks after. And if you look at this pie and you kind of look at all the bits that are connected with air conditioning, you can see that there's more than 50% of the energy use that the owner is looking at, which are in some way connected to air conditioning equipment. So what exactly is air conditioning? And I think all of us know that, but a really quick introduction. In warm climates, Australia is kind of moderate and warm, you are cooling most of the time. So you are delivering into a zone or a space or a room cool air, particularly if you're using all air systems. And this cool air picks up heat. There are two kinds of heat that we all know of, sensible heat and moisture. And then, of course, this air is returned somewhere. And that somewhere is the rest of the system. So here's your zone. And in your zone, you can have a VAV system, an underfloor system, an active chill beam system, a fan coil system, whatever it is. But then there is a loop that feeds air. You exhaust some, you introduce some ventilation air. This is the supply air that's going into the room. You cool the coil through which you pass the air. This cooling of the coil takes place in a large system with a water-cooled chiller. The chiller has a refrigerant cycle in it. And to cool the chiller, you have a cooling tower. So essentially what you're doing is you're taking heat from an already cool zone, passing it through all these loops and chucking it out into the atmosphere. Now, there is one additional loop that is quite important for us as energy simulators, and that's the control loop. And I'll talk to why this control loop is important in a second. So let's have a look at our case study building. So it's located in a place called Wollongong. We're in Australia, so we're in the Southern Hemisphere. It is summer now for us, right? So this is Sydney. I'm sure a lot of you have seen pictures of the Opera House, etc. And Wollongong is about 85 kilometers south of Sydney. And as you can see, it's quite very near the coast. The building itself is not particularly noteworthy. It is a bog standard ground plus 5-year-old rectangular building, which is what makes this case study all the more interesting. It has reflective blue glass, which was popular in the time when it was constructed. Was owned by a real estate investment trust fund called Folkestone. And at the time we got to it, it was already 25 years plus old. It was tenanted completely by federal and state government agencies, and that was one of the reasons why the owner was looking to get a good neighbors rating, because most governments have already mandated that they should stay or lease in high neighbors buildings. And it was performing quite poorly. It was sort of around the average of 2,000 of buildings that were built around or were operating around the 2000 time frame. And by the time you were 25 years old, your major HVAC plant is about ready to die, and there was a need for a complete upgrade of the plant. So there was a team. The owner hired us as the engineering team. There was a mechanical contractor, controls contractor, and an energy manager on site as well. So we then started to look at the building, and one of the first things we did was build an energy model or simulation model. And if you look at this sun path diagram, you can see very clearly that in summer, which is December, January, February for us, by the time it's 10 a.m., the east facade gets full sun. There's no real shading from the surrounding buildings. This is the north facade for us in the Southern Hemisphere. That's the sun-facing facade. Now, the model was used first to do some sizing of equipment. Okay, now I've shown you a very simple model, very simplified model. There was a lot of internal partitions, etc. We didn't really worry too much about that. We looked at the way that the air conditioning system was set up. We could see that there were 4 perimeter air handlers and 2 internal air handlers. We went and had a look at the building, decided on some reasonable inputs for the simulation, worked out what the lighting power densities, etc. might be, tried to find some old documents. There weren't any. So we made some engineering judgments. Okay. Now, sizing was the first thing we did, and there's a reason for that. There's a paper that I published in 2017 for the IBPSA conference in San Francisco, and I said that right sizing is the basis for an energy efficient design, but you really need energy simulation to understand how the performance of your building is going to be, what's going to come out of the meter, in fact. But all of this obviously is not very useful unless somebody's had a go at the building envelope before the mechanical engineer gets to it, because otherwise the mechanical engineer is simply putting band-aids on a poor design. Anyway, when you run a simulation, you can pull out hourly thermal loads for the building, and these blue lines are that, right? This is for cooling. And if you look carefully, and you can see some shaded red spikes, and that's the heating. Now, Wollongong is a very coastal town. It's quite a moderate town, so there's hardly much heating. Most of it is in the cooling part. Now, this is what the simulation predicts as hourly loads. When you do sizing, or when air conditioning engineers do sizing, usually we're looking at a much bigger system because there's a couple of safety factors. You're using quite an extreme weather condition, etc., to do the sizing. And if you think about it, an energy efficient air conditioning system, the job of an energy efficient air conditioning system is really to try to capture this difference. You have a large system in place. You only need this much capacity at that hour. How can you provide that in an efficient manner? So this energy use is actually what you can save, okay? And that's because by definition, when you size a system for a 1% confidence level, air conditioning engineers know what that means. It means that the 1% weather condition will not be exceeded by more than 1% of the time. And that simply means that for 99% of the year, you have more capacity than what the building requires. And that leads us to the statement about an energy efficient air conditioning system being able to wind back in an efficient manner across all parts and conditions. And that's where the control loop comes into its own. You have lots of options. You can slow down fans, you can make the water less cold, you can and you can change dampers around, you can vary the volume of air being put into a space. All kinds of options are available. But which ones should you choose for a particular building in a particular climate? That's the trick, I guess. So if I took these blue predictions and I put them into a duration curve, rank them from highest to the lowest. And if you look at this blue line, this is for Sydney, not for Wollongong. It tells me of my installed capacity, how much do I need for how long? And one of the craziest things that we found in many of the moderate climates that we work on, for Sydney, for example, is that from about this point to that point, typically an office building runs about 2,600 hours. So you're saying that about 1,400 hours, that much, I only need 10% or less of my installed capacity. Okay, that means for about 46% of operating hours, I need only 10% of my capacity. That's quite crazy. The last thing we did was look at the weather. So here's my weather file. Here's my design conditions. This is my dry bulb priority design condition. This is my wet bulb priority design condition. And what it tells me is that in Wollongong, I rarely have high temperatures, more than 30 degrees centigrade, you can see. Not too much, because there's temperature on the x-axis, there's humidity on the y-axis. But boy, is Wollongong humid. Typically, in an air-conditioned space, an air conditioning engineer is aiming for somewhere around 8 to 10 grams of moisture. Okay, so you're looking at somewhere around 24 degrees centigrade to about 20 degrees centigrade. You can relax it a bit or tighten it a bit, but and you're looking around that 50% relative humidity line, somewhere around here. You can see so many points in the year are above that. So my air conditioning system needs to be efficient, certainly at cooling, but definitely in dehumidifying the air that's going to come in. And that led us to what kind of system should we propose? And we designed an air handling unit, something that brings air-conditioned air into the spaces. And we had a dual coil system. So we have a fat coil, many rows. It takes the outside air. So the hottest air meets the coldest water. So you have the most efficient heat transfer. You drip all the moisture out at that point. And then that cold air you put into the mixing box. And there's a trim return air cooling coil. And there's a trim heating coil in case the air gets too cold. Okay. That's kind of like the magic box, if you wish. Now, using that information, we built an energy simulation model. Now, this is a simplistic representation of the real model. The real model had 2 chillers, 2 boilers, 6 air handlers. What I've done is I've got one of the 4 perimeter air handlers shown here and one of the 2 internal air handlers shown here. And you can see on this internal air handler, I've got now 2 cooling coils, the outside air cooling coil plus the one after the mixing box, the return air cooling coil. Okay. And there's a variable air volume damper in the zone. Anyway, the long and short of it is that we did some predictions, decided where the energy numbers should lie, went ahead and ordered new equipment. So here's chillers. And you can see here what we did was we didn't buy the most expensive or the most efficient chillers. And the reasoning behind that was because it was such a humid place, we wouldn't get a lot of what we call condensing water depression. So you wouldn't get cold condensing water temperatures because of the humidity in the air. So we didn't really need the most efficient chillers. We needed good and efficient chillers, but not the most expensive ones. Instead, we spent more money, and I apologize for the blurry picture, but this is a big air handling unit. And you can see here return air coming from the building, supply air going to the building. Now, this is fairly conventional. Here is the chill water coming into the coil section of the air handler. Here's the chill water going back to the chillers from the air handling unit. Okay, this is the fan section. We have a trapdoor there that you can open. But if you look on the other side of the same air handling unit, this is the magic box. Okay, this is a box that takes outside air from the open louver grills. It has its own chilled water connection. So this is where you get the coldest water hitting the hottest air and getting a really efficient heat exchange over there. So once that was all done, it was constructed, commissioned, we watched the meters, we collected the data, and at the end of 12 months, we went out and got ourselves a neighbor's rating. But this was the measurement that we had. So this was before the upgrade, and that was after the upgrade, taken directly from the utility meter, which the building owner had to pay. So we're only looking at base building owners' energy use. We're not looking at tenant energy use here. And before we came to the site, the building owner had already done quite a lot of other upgrades. He had upgraded the lights in the car park basement and in the lobbies. And so he'd done quite a lot of the simple things. So this change was literally only because of the air conditioning upgrade. Okay. Now, not only did we manage to get such a big reduction in the energy use, we also managed to provide quite a big change in how much electricity was being used, demand. And if you look, this is November. Again, November and December are warm months for us. Off-peak electricity is at night. Shoulder electricity is from about 9 o'clock to 4 o'clock. This is peak electricity, early morning and late afternoon. Okay. But what you can see is the amount of the demand of electricity, kVA as it's called, dropped 30% or so. Here we are, the numbers are here. But the energy use dropped in summer when the highest amount of cooling was required by more than 50%. Okay. Now, what's the benefit of doing this? Well, half the owner's bill in that building was actually based on the demand. How much demand is he using? And the way the electricity generator charges you for demand is he says that if you hit a particular demand number, like for example, in this case, about 425 kVA, and if you hit it once in a 15-minute slot, then you pay for it for the next 12 months. So if you can keep your demand down across the year, particularly in the summer months, a large component of your bill comes down. Okay. So these were all the things that we did. And obviously, once we got a certified neighbors rating, it was done by an independent neighbors assessor, that went from 2.5 to 5. Now, this case study is a few years old, but I like to use it because it was a time when the energy manager was in the building and we were allowed to be able to monitor and meter quite a lot, get hold of historical electrical bills, work on the whole process from beginning to end. That kind of project is not easily available in most cases. Anyway, a couple of things to understand is, no one is going to do this energy or greenhouse gas reduction from the goodness of their heart. They're going to do it because there's some money involved. So the financials were that, there was a $2.5 million spend, capital expenditure, for our carefully engineered end-of-life air conditioning plant replacement. Now, the financial visit in the real estate investment trust fund worked out that because of all that had been done, the value of the building had gone up by $4 million, and that was an instant return on investment. And they said that the value had gone up because of the savings in energy that we had shown on the capitalized value of that for X number of years into the future. This thing called an increased weighted average lease expiry. Because they were all government tenants, the owner was able to go back and renegotiate their lease. So they had 10 years of guaranteed rental income. And the guy tried to explain to me what this compression yield was. And for me, it was gobbledygook. But obviously, it meant something to him. And he was quite pleased about that. Reduced maintenance because the newer equipment didn't need much maintenance at all compared to the 25-year-old kit that they did have. And at that time, the building was one of the few, in fact, at that time, I think it was the only building that had a neighbor's 5-star. So, some insights from what we've done. Excuse me. You can, if you were able to do end of life plant upgrade, and that opportunity only comes about once in 25 plus years, you can really move the needle. You can really do a big reduction in carbon emissions, right? However, to get that big reduction, you must do a proper engineered solution. If you don't, you will live with the same mistakes for the next 25 years. Now, a lot of well-meaning engineers, particularly incumbent engineers who are looking after a building for its life, tend to do what is called like-for-like replacement. So you have a 1,000 kilowatt chiller, you're going to put another 1,000 kilowatt chiller. Actually, that is absolutely the wrong step to do. You need to resize equipment because over the years, everything's become more efficient. Lighting's become more efficient. You use laptops, which are using 44 watts. We used to use 200 watts for CRT machines. Most of your printers, fax machines, all of these things are starting to use less energy. If you're able to do a facade upgrade, your facade, particularly your glazing, can be enormously more efficient than the original. You really must do a rerun of the sizing and then work out what is the best outcome. In our case, we looked at the weather. We knew it was a humid place, and therefore we then thought about what needs to be done. So that's the only extra fee that the building owner will have to pay up front. But that's the hardest one to get because no one really wants to pay up front for something he's going to get in the future. That's a difficult one to always get. And that's where the mandatory regulations become useful. That drives these sorts of upgrades. It's important to remember that any upgrade, if you're going to change an old chiller to a new chiller, you will get some savings. New equipment is more efficient than old, but only if you do a well-engineered design will you be able to get the maximum amount of reductions and improvement in comfort and in internal air quality. Okay. Now there's a couple of, I'm going to take another 5 minutes. There's a couple of interesting post things that happen. About a year after we finished the cooling plant upgrade, the building owner wanted to improve or do the same thing for the heating hot water plant. So we had the model. We knew what size we wanted. So when we started to talk design, there was a incumbent engineer who suggested a size of plant, and we suggested a much smaller size in plant, and then we had to do a bit of negotiation, and we ended up somewhere in between. And in the first instance, there was no upgrade to the tenant side air distribution system. In the second tranche of upgrades, there was some work that we could do to resize and re-put some properly sized wavy boxes in there as well. And that lifted the performance even further. Now the building's been traveling at 5.5 stars for, I believe, the last 5 years, as far as I know. So that's a huge change. You're looking at 60% greenhouse gas reductions from the original design. And then, of course, all of these things ended up with a lot of financial transactions happening. The smaller real estate investment trust fund got bought by a bigger fund, and the bigger fund actually sold the building, and they realized that increased asset value. Of course, we only got paid our fee for service. Others that have been retired by now. And then the same guys brought us in to start looking at a hotel. And we helped them do a concept design for 2 out of their 5 guest floors and some of their conference facilities. And we're already seeing a measured 23% drop in energy consumption. So you can do this. It's just a matter of being able to drive the engineering and using the new tools to size and to do predictions in a practical way to come up with numbers that will be reflected at the meter. So I'm going to leave it there. I think I've used up about 35 minutes. Happy to answer any questions. Let me stop sharing for the present.
Thank you so much, PC. That was fascinating. We've got some questions in the chat already. And I know I have some of my own as well, which I might squeeze in if we've got time. But could you, a couple of people have asked what the pre-upgrade HVAC system was, if you could just explain that a little.
Sure. So if you remember that loop of air conditioning system bits that I showed you, you've got a plant side, you've got a system side, you've got a zone side. So the plant side was using some really quite old technology. They're called stack chillers. I don't know if you know what they are, but we replaced them with screw chillers. So yes, that's probably the answer to the plant side. The air handling side, the system side, was we took out some really old fixed large fans and replaced them with modern air handling units with variable speed drives, with close control of the air temperature and humidity, as I showed you. We weren't allowed to go into the zone side because they were very worried about disturbing the tenants. So all the work on the plant side and the system side was actually done at night and on the weekends. And because it was an old building, we had very large plant room sizes. So we were able overnight, or literally almost overnight, we were able to switch from the old system to the new system and then demolish the old system and take it out. So it was quite, there's a lot of, there's a bit of logistics involved to do all of that. Yeah.
That's absolutely fascinating. I think off the back of that and the really remarkable reductions, there's another question asking if you believe that achieving net zero carbon emissions by 2050 is feasible, and whether there are any more practical roadmaps like this to net zero that you'd like to share.
Well, the technology is definitely there. It has nothing to do with not having the technology. Whether there is the will to do it, I think is probably maybe a different thing. If you look at the IEA reports, I'm trying to see if I can find that. There was a graph that here we go. I found that another one of my presentations. Let me just share my screen here. You will see that, here we go. Where is it? Sorry, give me 1 second. Okay, if you can see the screen, this is an IEA study that came out. It's the literature review here. You can see that they do suggest that our activity, which is going to use a lot more energy, is going to almost double by 2050. But we're going to be able to reduce our greenhouse emissions by 97%. But the two big bars that you can see are, one is electrification, going from gas to electricity, and then energy efficiency. And the reason is, if you do electrification and then you are able to decarbonize the grid, that's a big, huge step. And energy efficiency is energy efficiency. It never goes out of style. We call it greenhouse gas mitigation or whatever you want to call it. If you don't do energy efficiency, then you're holding a leaky bucket, and you're going to have to constantly keep filling it. But if you have an energy efficient building or system or whatever it is, then the amount of energy that you need to use for whatever activity it is going to be less. So technically, there's no reason why we can't, but whether governments will have the wherewithal to force or mandate these requirements. And the only way it can be really done, as I've showed you using the neighbor scheme, is to find some way that the financials are affected, impacted, reputations are impacted. Then we will see change. I believe the UK has just picked up the neighbors rating scheme in the last couple of years. So hopefully that will drive. So if it becomes mandatory in some way, that'll certainly drive office building energy efficiency. We are beginning to see similar outcomes in shopping centers. We're pushing hard for some mandatory regulations in hotels. And if that happens, that'll be a huge change in hotels. I'm speaking only about buildings, of course. And then there's a big push from a lot of state governments to try and get to net zero. So renewables are being encouraged. Electrification is being encouraged quite significantly in Australia.
Thank you. That's a very comprehensive answer, and I think a very similar picture across the world. This is not a problem of technology, but it is a problem of incentives and willingness to take action. I have another technical question for you now, which I will try to get right, which is, did the pre-upgrade system have two cooling coils, an air handling unit and a heating coil in the zone group as well? And if it did, would not extra cooling the air to cut down humidity and then heating to achieve desired comfort be inefficient? Were there any other ways to deal with the latent load?
That's a very nice question. Okay, so the answer is that no, the existing system, the old system, only had a single coil, cooling coil, and a single heating coil. And the further answer to that is, although I have two cooling coils there, I don't need the heating coil, okay, for a large amount of time. And the reason is, yes, I overcool the outside air that's coming in, or the ventilation component of the air that's coming in, but that then gets mixed to the return air coming back from the zone. And that actually provides the free reheat that I need. That's why it's so efficient. If I had to reheat, then obviously efficiency would have been compromised. But that's a really good question, whoever asked that.
Yeah, thank you for that question. And now another question. Was there any difference in the occupant schedule? Did anything else change apart from the plant being changed?
No, this is pre-COVID, so office use was fairly similar before and after. And the building was fully tenanted, by the way. Mm-hmm. It was pretty, I don't know what happened after COVID. I have to go back and have a look at it. But the numbers that I'm showing you are pre-COVID, and the building is fully occupied. So no change in the occupancy.
Thank you. And I had a related question, which was whether there had been any change to the building fabric at all. Your leaky bucket analogy. So if this was a leaky bucket, it's still a leaky bucket.
It is still a leaky bucket. There is not a stick of insulation on the fabric. This was 25 years, 30 years ago now. So we only had energy efficiency regulations for buildings come in 2005 for commercial buildings. So before that, there was acoustic insulation where there was noise, but there was nothing else. And it had a really interesting glazing specification. And that was that we found that on all the sun-facing facades, so for us, the east, the west, and the north, which would be south in the northern hemisphere, there was double glazing. But on the facade that gets no sun, which, we had single glazing. So it could be that Wollongong is a really moderate climate, and it was felt that there was very little heat loss from that facade, but that's how it was, and it still is. But yes, not a single stick of insulation on the facade there.
So that's remarkable. So there's potentially still some further energy efficiency savings to be achieved with this building, albeit not without significant disruption.
And expense. Changing a facade, upgrading a facade is disruptive. Well, actually, it's not that disruptive. On one building that I worked on, we recommended, the ground floor had been designed to be shops, tenancy shops, but they had converted it into offices. And the facade was single glazing, and people complained bitterly about being too cold. So we actually found a contractor, we did some numbers, worked out a performance package. He came in every night and he did 4 or 5 meters every night, and he put an internal skin in there. So by the time it finished, all of a sudden, a lot of those complaints started to dry off in winter, which is very nice. But it is quite an expensive exercise to do, and particularly because if the original glazing is old, it is quite poorly performing glazing. New insulated glazing units, IGU units, of course, as you guys all know, are significantly more efficient. And you won't get that by doing what we did, which was to add a second skin with an air layer in the middle.
But presumably there is a point at which the glazing will be life expired, and in the same way as you've done with the HVAC plant, there's now an opportunity to have a significant improvement rather than a like-for-like replacement.
Yeah, most buildings, well, the kind of standard definition embedded into the construction code sort of leads us to a design life of somewhere between 40 and 60 years, depending on who's reading the text. So you expect the structure and the facade to last for that long. But our understanding is that, at least in Sydney, electric lighting systems, the churn is about once in 7 years. Big mechanical plant, the churn is about once in 25 years. So yeah, buildings keep getting refurbished. And if there was a way to drive that refurbishment against some target, and that's what Neighbours allows us to do, then you can certainly make a big change in how you do that.
That's fantastic. Can I ask one last question, which is, actually I might go for two, because one more question has just popped up in the question and answer box. And it is, what type of renewable energy source combines the best with air conditioning systems in warm climates?
Yeah, I mean, look, PV systems certainly, because your highest heat load is when your PV system is generating at almost its maximum power output. So that's a really in warmer and more moderate climates, certainly. In cold climates, obviously, that doesn't work very well. And also, if you have buildings that are running 24 hours, then PV systems are, unless you've got some form of storage, that's not really the best outcome. Wind is variable. I think it's used now, it's come down to combinations plus storage. So a bit of wind, solar, storage, something hydro as used as storage, pumped storage, whatever. I think the control systems that do the necessary things they're the ones that are, the grid needs to be adaptable. The old grids, we're having a lot of difficulty with our grid in Australia because it was designed for having, just a few generators at different points. And now you've got millions of roofs generating solar in the daytime, and that's difficult to handle. Yeah.
And the final one was really about future proofing, and whether you talk about sort of right sizing the plant, and did that involve right sizing it for a warming climate as well as taking account of the increased efficiency of appliances and so on within the building?
Yeah, me and my wife, she's a professor in sustainable architecture in another university. We have constant fights about this. So she talks about sufficiency, efficiency, and resilience. And I think the sufficiency bit sort of comes in at that point. When it's 45 degrees outside, do you need 24 inside? Or can you do with 26 or 27 or 28? In that case, you don't need to change the size of your plant. But if you want 24, that's a different story, And the other thing is that as the climate warms, what we are seeing, and people have sort of talked about it, and they're probably more qualified to talk about it than I, is that you will see these extreme events when you might have 2 days or 1 day of an extremely hot day, and then the temperature will drop. And then the reverse as well. Although we're going into a warming climate, we do have extremely cold snaps in this, this winter for us in Australia is nothing like what you have in the UK, but we still had cold snaps of 1 or 2 days of unseasonably cold weather. So one of the problems we're having is that our new code is being designed using future weather file, and we're going, that might not be the best outcome because you can't catch these extreme events. You need to have some way of measuring resilience of the building during those extreme events. And how do you measure energy use across the year? So both of those things probably need to be accounted for. I don't know the answer, but
No. It sounds like possibly a topic for a future webinar, I think. Speaking of which, I'll just use the last couple of minutes to tell you about what's coming next. Before the end of the year, we've got another of these building simulation best practice webinars, this time focused on new builds, and it's Nishesh Jain, who will be talking about design stage performance modelling. So this is aimed at sort of early career practitioners, people looking to understand how to apply simulation in a consulting role. And then we have, in the new year, we're going to continue with our urban building energy modelling series, but moving on to a much more practical focus and demonstration of tools. So there's another couple of webinars there and more in the pipeline as well. But the main focus of what we're doing in the new year is going to be on occupant-centric simulation-aided building design, with a whole series of seminars which we will be launching registration links for very soon, and that's going to run from January to June. Now, this webinar has been recorded, like all of our webinars. It will be available on our YouTube channel, so that's IBPSA University, and you'll find, I think we now have with this, I think we'll be up to 53, perhaps 54 recordings we have there, which is an absolute masterclass in building performance simulation. So do check it out. A number of the webinars have some additional links added in the in YouTube for extra information. And finally, I would just like to say we are approaching that time of year when people's minds turn to gifts that they could be buying for the special people in their lives. And perhaps one suggestion might be a supporting membership of IBPSA, which would allow you to support the work of IBPSA in making all of this amazing content available free and to anybody who wants it. You'd also get, depending on the subscription you choose, print subscription to the Journal of Building Performance Simulation, and everyone would have online access to the journal, and you get the right to use the IBPSA supporting member logo. The fees are remarkably cheap. These are still at pre-COVID prices. So do consider that, and you can find out more at ibipsa.org/membership. But with that, we'll close. Thank you very much to PC. That's been fantastic. I've really enjoyed that. I'm sure the audience have as well. And thank you to the audience for all your excellent questions. And I do hope you're able to join us again soon. Thanks.
Thank you for the opportunity. Bye.
Thank you. Bye.